So, welcome back to this NPTEL course on tribology of materials. In this lecture as well as the following lectures, I will introduce you to one of the newer concepts and newer understanding of the tribological properties of materials. As the slide says that first I will give an overview of the cryogenic wear of materials. So, cryogenic means here I will be discussing particularly how the friction and wear properties of several materials are influenced because of the change in test environment from ambient to liquid nitrogen environment. So, for that one has to have a very special test trick, and with this test trick one can evaluate the friction and wear properties of different materials. So, first I will give a brief background, then that will be followed by design of what I say cryotribometer. Like for high temperature tribology, we need to have a separate tribometer. Similarly, for cryogenic testing facility also we need to have a different test facility. Then I will give you some illustrative examples of the wear test on metals like stainless steel, titanium, copper, followed by alumina and zirconia in the next couple of lectures, and silicon carbide, and then I will conclude. So, typically for cryoturbo pumps, which is used in the space shuttle main engine, those kind of very critical engineering very critical engines, they require Martensitic stainless steel bearings, and this Martensitic stainless steel is typically 440C grade. At present, bearing life is restricted because of the extensive wear and spalling, because of the high speed sliding conditions under high contact pressure. However, if we want to explore new materials to replace the 440C steel bearings, one needs to have suitable experimental setup for high speed cryogenic tribometers. And limited research activity in the cryogenic wear is currently being conducted at NASA, ESA, European Space Agency, and NAL, Japan. These are the laboratories. What are the operating conditions in this cryotribometer? This operating conditions typically is liquid oxygen environment, mostly it is unlubricated contact conditions, and there is a micro slip at a typical contact stress of around 2.1 gigapascal. So, 2.1 gigapascal, that is fairly high contact stress, right? And oxidative wear limits the life of these 440C bearings, and typical shaft speed at which the sliding takes place is 30,000 RPM. 30,000 RPM is extremely high sliding speed, and there is axial loads somewhere around 3,600 to 4,500 kilogram force during startup and shutdown. So, therefore, against this backdrop of this requirement, the requirements for space bearing materials include it should have a low coefficient of friction and also high wear resistance, and high wear resistance leads to longer life. Hardness is required to ensure high wear resistance, and properties should be retained at low temperature, excellent thermal shock resistance, and high compression strength. High compression strength is required because, as you have seen in the last slide, I have mentioned 2.1 gigapascal is the typical contact stress. So, in order to sustain that kind of high contact stress, the materials must have high compressive strength. Now, here goes the typical composition and other properties of 440C bearing space bearing materials. The composition is around 12 to 17% chromium, 1 to 1.8% carbon, fairly high carbon content, and it has manganese, moly, silicon, and phosphorus. It has a hardness very high, around 58 to 63 in Rockwell C scale. Yield stress is around 1.8 gigapascal, high corrosion resistance and high resistance to chemicals. But however, the problems with 440C is that typically if you do this wear test, the surface layers of the wound surface appears white layers, and white layers means it is essentially iron oxide, with some FeO and martensitic alpha prime material, and there is absolutely no Fe3O4 or Cr2O3. And white layers are formed by a combination of surrounding high temperature and cyclic deformation. And there is a considerable depletion of chromium due to the oxidation of chromium oxide at around 1000 degrees Celsius to CrO3. So essentially Cr2O3 that goes to CrO3 at 1000 degrees Celsius. So this kind of oxidation, so this kind of oxidation takes place at 1000 degrees Celsius, and that evaporates at more than 900 degrees Celsius. And metallic chromium is also susceptible to evaporation above 900 degrees Celsius. Now essentially these white layers that leads to selective oxidation of silicon to form silica, and also iron oxide can form a double compound called FeO Cr2O3 at 1344 degrees Celsius. Now all these eutectic liquids, like low temperature liquids, that may give rise to dendritic solidification, which is very characteristic for many of the metals and alloys, and contact temperatures are high enough to cause localized surface melting even when bulk temperature is at the room temperature. Now what are the alternative materials? Alternative materials is certainly silicon carnitrile, silicon carbide. These are like ceramic materials, extremely resistant to oxidation, particularly at such low temperature. It is 30% harder and 40% lighter than steels. As you see, these numbers indicate that these materials, while being lighter, it is also harder. Harder means it may have good abrasion resistance. So what are the different coatings like lead, silver, gold, PTFE coatings on 440C material, and SLC, so polymer based solid lubricant coatings. SLC stands for solid lubricant coatings filled with MOS2, and it has a constant COF throughout its life. And DLC is another material, that is diamond like carbon coatings, and these are made by vacuum arc deposition of filtered high speed carbon plasma fluxes. Okay, and this has an extremely low value of wear rate under cryogenic conditions. Now this is the custom designed cryogenic wear tester that we have developed and designed way back, more than a decade back, as part of our space tribology program with Indian Space Research Organization, ISRO. And what it typically does, this particular shaft and pulley arrangement allows to experience, allows this disc and pin assembly to experience extremely high relative motion, and the rotational speed of the disc can go up to 36,000 RPM. And 36,000 RPM is certainly sufficient to simulate the space bearing applications, as I mentioned a few minutes back. The load is somewhere around 2 to 20 Newton. This load, it can be varied by dead weight, and then one can record the friction coefficient at very high sliding speed conditions. So this is kind of a very unique cryogenic tribo tester. The other things I must mention you, that this entire assembly is dipped into this particular cryo chamber, and this cryo chamber there is a constant flow of liquid nitrogen, so that at any given point of time this particular assembly is completely immersed in liquid nitrogen, and that is very important, because liquid nitrogen, if it is filled up in, if it is submerged in liquid nitrogen, then only we can simulate that cryogenic sliding conditions. This is much more detailed design of this cryogenic tribometer. You can see this is the main region. This is the cryogenic chamber, and this is the motor and gearbox. This kind of motor and flexible shaft, and this kind of assembly, external assembly, allows the disc to rotate at extremely high speed. So one of the problem with metals also, that in cryogenic conditions the metal can undergo ductile to brittle transition. This is called DBT. Those who are from metallurgy background, they know that DBT leads to catastrophic failure at sub-zero temperature for many of the metals. But that certainly would not be the case for ceramic based materials, because ceramic based materials, unlike metals, they do not have ductile to brittle transition. So what are the materials that we have done the experiments when we started the space tribology program? First set of materials we did is the 304 stainless steel and 440C martensitic stainless steel. The load is 2 Newton and 7 Newton. We cannot do this test for extremely longer time period, longer sliding time, but certainly at 5 minutes to 10 minutes time. Sliding speed was varied 0.89 meter per second to 22.4 meter per second. So, that is extremely high sliding speed. So, you see that this is that the circle ones is the 304 stainless steel, this is for the circle one, this one is for 440C martensitic stainless steel at a 0.89 meter per second, and you have this 2 Newton, and when you increase the speed, you see that typically at higher speed the coefficient of friction actually is lowered. So, one can get extremely low coefficient of friction at around 0.08 at speed of 22.4 meter per second. That typically stainless steel, they are for self-mated stainless steel. If I am talking about the self-mated stainless steel at room temperature, the COF is around 0.5. So, this is at 0.5 at room temperature, but at liquid nitrogen temperature at a high sliding speed conditions, as you can notice here, that coefficient of friction almost reduced 5 times less. So, 0.5 to less than 0.1. Okay. So, these kind of things, this is one of the important observations here. Now, when you do this when we have done the other experiments like self-mated 304 stainless steel, and 304 stainless steel here COF is 0.1, and in 440 stainless steel COF is 0.15 to 0.25. So, it is very clear that at liquid nitrogen cryogenic temperature the frictional behavior is significantly influenced. Now, if you look at the wear rate of these materials, if you look at this, as you increase the sliding speed, the wear rate is essentially increases for particularly for these three materials where self-mated SS304 steel is. Hydrogen contact stress is 0.6 gigapascal, which is not very low value, it is fairly high value, and so essentially your coefficient with sliding speed, your coefficient of friction is reduced, but wear rate increases. At the fairly initial lectures of this NPTEL course, I have mentioned that coefficient of friction and wear resistance they are not directly correlated. What it means, what I made it very categorically at that point of time, that in a tribocouple may experience low coefficient of friction, but the same tribocouple can experience high wear rate. Similarly, a tribocouple may experience extremely high coefficient of friction, but the same tribocouple under the identical conditions can experience low wear rate. So, these are like, it is not directly correlated. Now, if you see 304 stainless steel, when it is 2 Newton its load and sliding speed is 17.4 meter per second, and this is a typical how this wear track sliding wear track they look like. And if you look at this a little bit, if you look at the higher magnification optical microscopy images, you can clearly see this, because the sliding is taking place in this direction and there are cracking. Most of the cracks, they are oriented perpendicular to the sliding directions, which is quite expected, because the tensile stress direction, the cracks always propagate around the tensile stress directions. In 440C martensitic stainless steel, we do not see any observation of cracking on the wound surface like what you have noticed here. Now, now I will just show you some of the other research results where we have used stainless steel 440C ball versus coated stainless steel 440C disc. So, what it means is that, so we have put these coatings, and this particular part of the research was done in collaboration with Professor Koji Kato's lab in Japan, and so you can use these gold indium phosphate coatings and silver indium phosphate, and these are the coatings. These are obtained from NTN Bearing Company, Japan, and this coating thickness is typically 0.7 micron. So 0.7 micron coating is fairly thin coating, and they have a different grade of coatings, like from TR Coatings UK also we have got MOS2 titanium SIP coatings. So what are the different operating parameters? Different operating parameters is that you have a ball as SUS 440C steel ball, you have a disc different solid lubricant, your normal load is around 1.4 gigapascal, and your sliding speed is 0.67 to it can go to up to 1.67 meter per second. Now let us look at this a summary of the coefficient of friction results. What you notice here clearly, MOS2 with titanium, when it is coated on 440C, it has a coefficient of friction of 0.05. So 0.05 coefficient of friction is fairly small and fairly good values. Now if you have simple gold coating, the coefficient of friction is around 0.1 or higher. If you have silver coatings, this is 0.1 and above up to 0.17 or so on. So this is that mu average in 9,500 to 10,000 cycles, and different bars essentially indicate what is the sliding speed that you use in your sliding experiments. Now individually, if you look at the different material combinations, what you see that MOS2 titanium coatings which experience extremely low coefficient of friction of 0.05, here we have clearly see the transfer film on this materials. This is the wear track here. Similarly, formation of transfer film on gold coating on the ball is also observed on this particular material against stainless steel 440C material. The same is true for the lead coatings. On the lead coatings, and it is transferred it is transferred on the ball. So all these images are taken at certain magnifications of the ball owned surfaces. Now these are some of the results are published in Materials Science and Engineering A journal, and now I will show you that we some of the results that we have done, some of the results we have obtained with high purity titanium. Now this is that extremely high purity titanium, and this titanium is owned against bearing steel. Now by changing the heat treatment conditions in titanium, what we have done, we have, so these are that pure 99.9% purity titanium, which is cold rolled to 62% reduction in thickness, and then the same titanium is has undergone recrystallization annealing for 5 hours at 440 degrees Celsius, titanium 1, 500 degrees Celsius for 5 hours, titanium 2. So for 400 degrees Celsius is this microstructure, 550 degrees Celsius is this microstructure, and 650 degrees Celsius is this microstructure. So this is that optical images, optical microscopic images of the etched titanium surfaces. Now those who are from metallurgy background, they would clearly distinguish that this microstructure, they differ in terms of the grain sizes, and that is quite expected, because if you increase the heat treatment temperature, one would expect a corresponding change in the microstructure in terms of the length scale, in terms of the grain size, right. And the same thing you notice here the average grain size is 9 micron, and here the average grain size is 17 micron, and here the average grain size is 37 micron. So 9, 17, 37 micron. Now when we use these three different titanium surfaces, and we use another matting couple is steel, and if we use these three different microstructures, this would allow us to understand what is the influence of the grain size on the wear resistance properties. Grain size has direct influence on the hardness and yield strength of metals. So by using three different grain sizes, 9 micron, 17 micron and 37 micron, one would immediately expect that this titanium 1, titanium 2, titanium 3 would have different hardness and would have different yield strength. So if you have different hardness, particularly for metals, if the wear is dominated by the abrasive wear conditions, then one would expect a difference in terms of wear resistance. Let us see how our results look like in the next few slides. Now, in terms of frictional behavior, this is for the titanium 2. We are comparing here room temperature versus liquid nitrogen results at different sliding speed. At room temperature, there is certainly higher coefficient of friction. If you see that this difference here, it is 0.55 versus 0.35. So, this difference is around 0.2, and this difference is certainly reduced when you go to the high sliding conditions, particularly at more than 1 meter per second. And for cryogenic conditions, we have done extended experiments up to 5 meter per second, and where you can see the coefficient of friction is somewhere around 0.28. Okay, so it is certainly not very low compared to what you have seen earlier in case of stainless steel. Now, if you look at the other materials, absolutely grain size does not have any influence on coefficient of friction, and that is what is also expected. However, if you now plot wear rate as a function of sliding speed for 3 materials, titanium 1, titanium 2, titanium 3, the sliding speed influence you see, that is not much in case of the titanium 1, but titanium 2 and titanium 3, particularly this is for the titanium 3, there is a clear linear decrease in the wear rate with sliding speed. What it means that at higher sliding speed, wear rate decreases. That is not only true for titanium 3, but also true for titanium 2 as well. And this is the 2D stresses that what we get from the laser surface profilometer, and then what is this typical depth, like it is close to 50 micron depth, which is very significant wear. Now, this is quite an interesting observations. Now, those who are from metallurgy background, they know sigma is equal to yield strength for polycrystalline materials. Sigma is equal to sigma naught plus k d to the power minus 1 by 2, where sigma y is the yield strength of the polycrystalline material, sigma naught is the yield strength of single crystals, because from this you can clearly see that when d is equal to infinity, sigma y is equal to sigma naught. So, when d is equal to infinity, that means when grain size is extremely large, and if grain size is extremely large, you can consider single crystal materials, and in case of single crystals, your polycrystalline yield strength becomes single crystal strength. So, and d is your grain size and k is the Hall-Page coefficient. So, this is the famous Hall-Page equation, which most metallurgists they are fully aware of. Now, in line with this argument that since yield strength also has a proportional relationship to d to the power minus 1 by 2, we tried to explore that whether wear resistance, which is nothing but 1 by wear rate, has similar proportionality relationship with grain size to the power minus 1 by 2. And what you notice here, that they have very linear relationship at 4.19 meter per second, that is very higher sliding speed. This relationship also is valid at 1.11 meter per second and 0.67 meter per second, but this particular linear relationship between wear resistance grain size to the power minus 1 by 2 by far most significant in only at the higher sliding speed, because in this particular 2 data points you do not see much increase, but as you go to the higher value of grain size to the power minus 1 by 2, we do notice that wear resistance increases. So, this is one of the things that I have mentioned at the beginning of this experimental when I started showing the experimental results with titanium. So, titanium 1 surfaces, if you see that abrasion and ploughing, that you can see, and there is also delamination of the tribolayers that is also observed on this particular titanium 1 surface after sliding with liquid nitrogen. Other interesting observations that we have observed, that in case of titanium 2 at a particular grain size, we see that very spherical kind of nodule like of titanium oxide wear particles. So, these titanium oxide wear particles are trapped in these particular groups, and once they are trapped in these particular groups, it would lead to the third body wear. And other interesting observations that we have observed, that there is a extensive ductile deformation which leads to at some part shear lip kind of behavior, and the shear lip essentially leads to plastic deformation. It is the signature of the extensive plastic deformation at the lowest speed. So, we have done a systematic observation of the microstructure just to observe spalling and cracking, severe cracking in this case of titanium. Now, from metallurgical point of view, what is more important for us to show was to see the subsurface deformation and damage. And what you notice here, that this is the particularly case for one of the titanium materials, and if you carefully etch the surfaces, we do see in individual grains lot of twins. So, these twins are one of the deformation mode. For metals, there are two type of deformation mode, one is slip and one is twinning. So, this twinning, if you see, this is the large grain size like 40 micron or so, and you see these twins, they normally extend from one grain to another unless they impinge on another growing twins. So, for example, this twin cannot extend to the other end of the grain edge because it is actually interacting with one of the longer twins on the microstructure on this specific grains. So, this twinning is one of the mode of the deformation in case of the what we observed in the subsurface deformation in this particular case. Now, if you look at this particular wear mechanism map where we have shown the grain size versus sliding speed. So, what we have seen that at very low very large grain size, it is the cracking of tribolayer, whereas at very high sliding speed it is smearing of tribolayer, which is very important. So, this was published in Acta Materialia, which is one of the flagship journals in the field. The another one we have published in Metallurgical Transactions in. So, quickly few more slides on copper. So, titanium is one of the harder material, copper is relatively softer materials. So, we have done also a series of experiments, cryogenic sliding wear experiments on copper, and what you see here, this particular copper is again high purity copper, which is cold worked, and in these cold worked materials it is FCC copper. You can see that inhomogeneous feathery appearance because of the cold rolled state. Hardness is Rockwell B. It is not Rockwell C, it is 55 in the Rockwell B hardness scale. Now, we have varied that load 10 Newton to 20 Newton, and you can see at the higher load, that means higher contact stress, coefficient of friction drops and it is going to 0.1, and but at the lower load the coefficient of friction is fairly high, it is around 0.35. So, in terms of the wear rate, if you go to that higher load and then higher sliding speed, again that compared to the lower load, that wear rate is decreases, but decrease may not be very significant, but certainly there is a trend of decreasing, particularly if you look at this one, there is a trend in decrease with increase in the load as far as the wear resistance is concerned. So, the copper also again it undergoes some oxidation at the wear surface, and you can see here there are copper oxide particles which are also formed on the materials. So, this is this copper, and this copper, this is the sliding wear track, and this sliding wear track you can see that in the sliding wear track you can very clearly notice that there are signs of deformation ploughing. In this region you can see like farmers, they plough the field. Similarly, this during the sliding wear, the harder materials, they plough the softer materials, and this is one of the mechanism of the wear what we have observed in case of copper. Now, if you compare these two materials, titanium and copper, what you notice, the titanium case, with sliding speed the wear rate decreases. In copper, in the case of titanium with copper, we do not see any very clear trend. In terms of the flash temperature calculations, what we have observed that in case of the copper, because of the high thermal conductivity, flash temperature is fairly low, but titanium flash temperature is above 0 degrees Celsius or even above room temperature, for example here and here in titanium. So, because of the difference in the flash temperature, the wear rate was what you see in case of copper is fairly low. So, these are the actual calculated flash temperature for this specific tribocouple and we have also calculated the contact stress in this particular case by taking the titanium as 110 gigapascal, and we are getting contact stress is 537 megapascal. Now, we wanted to see that whether dynamic recovery is one of the possibility under high stress standing conditions, and for there we have calculated that what should be the dislocation, what is the dislocation density, we considered what is the grain size in case of titanium, and what is the Burgess vector of the dislocations, and these are the fraction of the active edge dislocations, and what is the strain rate corresponding to the sliding speed of 1.1 meter per second. So, what we have found that value of tau shear stress is around 1.45 10 to the power minus, not tau, this is the this value of tau in this particular equation is 1.45 10 to the power minus 4 seconds. So, it is at the rate of, it is even the less than a millisecond. So, for higher sliding speed tau value will be even be smaller. So, this work is published in Journal of Material Science. Thank you.